So the second, slide here, we have note 2. What does note 2 says? Note 2 says that the square root of 0 is equal to 0. So each and every time you have the square root of 0, it will give you 0. Don't forget that. But when you have the square root of a negative number, it is completely impossible. At this grade, the square root of negative number, it is impossible up to grade 11. But from grade 12 and upward, it is possible to solve it. But at your grade, just remember, it is impossible. You cannot have a square root of a negative number. So each and every time you encounter this, just say it is impossible. But for the 0, it gives you 0. Then we go ahead. The above definition of the square roots demonstrate that there is no existence of a fraction equal to square root of a. I mean that the square root itself will not gonna give you a fractional number. No, it's gonna give you a whole number, not a negative number. There might be let's say a square root, as a fraction, but there is a way to solve it. But the result will not gonna be a fraction. The result will mostly be a whole number most of the time, except there is still some exception. But for the moment, let's stick to this idea. And square root of a is not a rational number, rather an irrational number. So remember that different sets when it comes to numbers. We have n, n prime, and we have q prime, we have r, and we have c. All right. So in this case, the square root lies in the sets of irrational numbers, which means the q prime. The q are rational number. The set q is identical to rational numbers, and into bracket it says cannot be written with a numerator and denominator as integers. Okay. So the thing is that you cannot write a square root, under this formula. You go ahead, you say square root of let's say plus 3, or let's say square root of minus 5. You cannot write a square root this way because this is already impossible. This, yes, it is acceptable, but don't write it with the plus. You just go ahead, you say square root of 3. This phrase basically say, because remember an integer, the integer is a number, it's a whole number that takes both a positive negative sign, right? The number can be positive, negative, or 0. That is called an integer number. But in this case, you do not have to write a square root as an integer number. You have to write it as the square having the radical symbol and the radicand. That's it. It has to be a radical this way, not with a plus in front, neither a minus, right? So yeah, let's keep going. And then we go ahead. We have here, okay, it says when a and b, two positive numbers defined as a strictly greater to 0 and b greater to 0, and we have square root of a plus square root of b. Remember that this expression is different from square root of a plus b. These are the lines to understand. These are the lines to grasp. That's why, you see that, I've put them, they are vibrant, yes, that's why they are vibrant compared to other, font. So these are the one you have to understand to be able to solve exercises, to be able to come up with a solution that will give you marks and the better understanding of the subject, right? Yeah. So it says this, right? It says when a and b, two positive numbers defined as a is totally greater to 0 and b is totally greater to 0, square root of a plus square root of b are different to square root of a plus b. It is completely two different expression. Completely two different expression. And when you have a and b, two positive numbers defined as a totally greater to 0 and b totally greater to 0, and you have the expression square root of a times square root of b, it is equal, it is the same as if you write them square root of a times b. It is exactly the same thing. Do not get confused between this expression and this expression. They are different. We have addition here, or might be a subtraction. We are having multiplication. So what we have is that there's a difference in solving square root operation between the addition and subtraction to multiplication. Do not confuse them. And the last line says that when a and b, two positive numbers defined as square root of b over a, and which is equal to square root of which is equal, or it can be written as square root of a over square root of b, and you have a different to 0. So meaning that each and every time you have the square root of a fraction, which means b over a or a over b, just remember that this expression, it is equivalent, it is equal, or can be written as the square root of b, the square root of b over the square root of a. And you're gonna have a, the number a, to the denominator, which is different to 0. It's not gonna be 0. It's gonna be another whole number, probably from 1 to 9. Okay, so yes. Then going ahead now, after understanding these three lines, then you can come down here, start solving these examples. You will see here we have here a square root of 4 times 25. By applying this rule here, if we have to apply this rule here, we are here, right? From here we can go here, or from here we can go to the other side. So we're here, so we are coming here. The square root of 4 times 25, it's equivalent to the square root of 4 times the square root of 5. Or the square root of 4 here gives you 2, and the square root of 25 gives you 5. 2 and 5 are called perfect square. Why are they called perfect square? It's because if I have to solve the square root of 4 this way, which is equal, remember we said that the square root of a, okay, the square root of a like this into bracket square, gives us a, right? And if I have to transform, right, this expression into this expression, this is how it's gonna look like. It's gonna look like this: square root. I know that 4. If I want to have a square at 4 has to become as 2 exponent 2, right? I have this the radical symbol here, and I have the radicand. I have the radical symbol and I have the radicand. This square here is the square here, right? So this gives me what? This gives me a, so it's gonna give me 2. Remember the example that I went through. I said that the square root itself means that the radical symbol has an exponent of half 1/2. So the 1/2 multiplies the 2 here. I will remain with the radicand, which is 2. That's what the result gives us 2. The same thing here. 25. If we want to write 25 as an exponent, 25 is 5 times 5, right? 5 times 5 in exponential gives you 5 square. Exactly. So 5 square, if I multiply the 2 with the exponent of that represent the radicand, it gives me what? It gives me 5. That's why we're having 5 here. Then if I go 2 times 5, it gives us 10. So the 2 and the 5, I'm repeating, they are perfect squares. We're gonna go through it as we go along the whole lesson, and you will understand. Then the 4 and the 5 are the square numbers. These are the square numbers. The 2 and the 5 are the perfect square. You're going to learn about them. Don't worry. We will be getting there. So, yes. Let me just wrap it a little bit, to clear the space, Yeah. So, as we continue, the same thing here. We have here square root of 5 times the whole square root of 9 times 25. Then if we have to solve it, we're gonna apply the same trick here because we are dealing with multiplications, right? Then we're gonna go, this expression is gonna become square root of 5 times square root of 9 times square root of 25. Square root of 25 we know already gives us 5. Square root of 9, remember we went through it. If remember in the previous slide, right? Square root of 9 gives us 3. So if you go back here, square root of 9 will give us 3. Then you will notice that square root of 5 still remains square root of 5. It didn't change. Why? Because 5 is not a square number. 5 is a whole number. Remember, I told you that 4 and 25, in this case, plus 9 at this moment, they are called square numbers. They're square because what? From them you can get a perfect square, or you can write them into an exponential expression. By that I mean that for 4, the exponential expression of 4, you know it, right, is 2 exponent 2. And exponential expression of 25 here, it's a little bit raggy, a little bit groggy there. It gives us 5 exponent 2, sorry. Then the exponential expression of 9 itself gives us 3 exponent 2, or 3 to the power of 2. Same thing, if come back here and click here, you can see all these. Let me just rub them off. What I will just return here. All these expressions, 9, 6, 25, 1, 21, 81, 144, 6.25. These are square numbers because from them you can write them as perfect squares. Okay, so that is the idea. That is the hint you have to understand. So as we go along, the same thing here. So the same expression, let's go back where we're at. We're here. We were here. So now you will notice that we have the multiplication of a whole number because 3 multiplied by 5 gives us 15. which multiplies the square root of 5. No, by that, what do I mean? I mean this. So by this expression here, we're gonna have 3 times 5, right? Which is 15. So we're gonna have 15 like this, multiply by square root of 5. Just remember that you have two different expressions here. You have the 15 and you have the square root of 5. You cannot go any further. You stop here. Because first, they don't have the same radicand. This is a whole number, this is a square root. And there's the multiplication here. So you keep them together. So the expression will become, the final expression will become 15 square root of 5. This is the final result. Or you write them 15 times square root of 5. But in mathematical symbolism, this is acceptable. This is, this is what is required, how to write it. This is acceptable, yes, but as you go, you pass, you go through different grades as your level progresses, writing like this for some teachers might be considered wrong. Trust me, I've been there. So take me as an example, as an exemplary, used to be student. Yes. So yeah, this is the best way to write it this way. So 15 square root of 5. If you go to the next example, we have square root of 5 times square root of 3 times 121. It gives you equal to square root of 5 times equal to square root of 3 times square root of 3 times square root of 121. Or square root of 3 itself, it's not a square number, because there's no exponent to 3. It's not a square number, it's a positive whole number, so it will remain the way it is. But however, 121, because if we go to the previous page, you will see that 121 as a square number gives you a perfect square of 11. Right? It gives a perfect square of 11. So if we go back here, so in this case, if we have to go step by step, here, if I try to decorticate this expression,